Welcome to Chapter 22, Cost Curves. Costs can be decomposed into two broad categories. There are certain types of costs that do not change as the level of output changes. Those we'll call fixed costs, and other types of costs to increase the output of the firm, those costs have to rise. So we will categorize those as variable costs. And Varian denotes those with the letters F and C sub V. So you'll notice that total cost is a function of output. Fixed costs are not a function of anything because by definition they're fixed. And then variable costs are also a function of output. I can divide total cost by output to get average cost. And then I can divide each of the components of total cost by output, and I get these other categories. Average fixed costs would be fixed costs divided by output. Notice that average fixed cost now is a function of the output level. Not because fixed costs change in output, but because we're increasing the denominator. And then finally, average variable costs are also a function of output. The short-run average cost curve must be U-shaped regardless of the functional form of the cost function. So, the way to see this is that average fixed cost must be decreasing in output. It has to be this exponential shaped curve. The reason why, you'll notice the functional form of average fixed costs. It's fixed costs F divided by output, and if you have a fixed numerator, you increase the denominator, the quotient is decreasing in the denominator. So average fixed cost must be decreasing. The way to think about this is, think about a firm that has a single unit of output. Those fixed costs, average fixed costs are enormous for that firm. In fact, it would be equal to the total amount of the fixed costs. But as a firm produces more and more units of output, the per unit cost becomes smaller because those enormous fixed costs are amortized over a larger and larger production run. One close and recent example that illustrates this beautifully would be the Giga Texas factory from Tesla. I was reading that the Texas Tesla Gigafactory is set up in such a way that no human hands touch a car as it proceeds through the factory. So there's no labor expense directly working on a Tesla car. It's in total assembled by robots or automated processes. So what that means then is that there are, of course, there are variable costs associated with steel and glass and batteries and all those other things, but with regards to labor, there are no variable costs. The cost per car is minimized by basically running Giga Texas 24/7. Day and night, every day of the year, Tesla is able to minimize its costs of production. The middle graph, average variable costs, must be upward sloping because of the law of diminishing marginal product. One example I could think of that might illustrate this, think about the Starbucks at Moody Library. It's a small Starbucks. It has a single latte machine. So, basically, if Starbucks wants to increase the output of lattes at this particular store, what they do is they start adding units, they start adding workers. So as they move from one worker who has to do everything to two workers, you can have division of labor, right? One worker can run the espresso machine, the other person can run the microwave, the cash register, take orders, glad hand customers. And then as you add more and more workers, you can get greater specialization and division of labor. Well, eventually, there gets to be so many workers that additional workers increase output by just a very tiny amount. And this is due to the law of diminishing marginal product, right? So if in the short run, Starbucks is stuck with the single small espresso machine that they have, additional workers will, the output that they get from each additional worker added to the production process diminishes. So I combine those two ideas together and I get this U-shaped average cost curve regardless of the functional form of the cost function. Okay. Marginal cost, you remember from the prerequisite course, is the additional cost that the firm incurs to produce the last unit of output. What we could say then is that the marginal cost of producing the yth unit of output is the total cost of producing y units of output minus the total cost of producing y minus 1 units of output. But since this is a calculus-based course, the natural way to compute marginal cost would be differentiating costs with respect to output. If I substitute in the definition of total cost having fixed components and variable components, you remember the derivative of a sum is the sum of the derivatives, and the partial of fixed costs with respect to output by definition is 0. Fixed costs by definition do not change in output, so that term drops out and I'm left with marginal cost being the derivative of variable costs with respect to output. Now if I put all these curves together in a graph, I get a graph that looks like the one that I've illustrated here to my left, and each bullet here represents a point to that graph that we can easily see. First is we have average cost curve, we have an average variable cost curve, but we don't illustrate average fixed cost explicitly. But it's still present. Average fixed costs are the vertical distance between average cost and average variable costs for any output level. The marginal cost curve bisects the minimum of both the average variable cost curve and the average cost curve, and I'll have a proof of that in the next slide. The marginal cost curve slopes downward initially due to gains from division of labor. So this was the story of Starbucks that I told in the previous slide. That as the Starbucks store goes from 1 to 2 to 3 laborers, what they can do is they can divide the tasks and have specialization of labor, division of labor and specialization, and that reduces marginal costs at least initially, but then the marginal cost curve eventually slopes upward due to the law of diminishing marginal product, which we also talked about. If the capital stock is fixed, the output that they can get from additional units of labor will eventually diminish. So we combine all that together and we get these 3 U-shaped curves like what I've shown here. The proof that marginal cost bisects the minimum of average variable cost, we know that the minimum of average variable cost occurs when the slope is 0. The slope of any function is equal to its derivative, so I could take the partial derivative of average variable cost with respect to output and set that equal to 0. Average variable cost I could re-express as variable cost times y to the minus 1. And then I could apply the product rule of derivatives, right? So the derivative of a product is the derivative of the first term times the second plus the first term times the derivative of the second. And then as I take those derivatives, I come to the next line. What I can do at this point, I can simplify a little bit because I could multiply both the left hand and the right hand of this equality by y, and then I get marginal cost marginal cost minus variable cost times y to the minus 1 is equal to 0. I move that negative term to the other side, to the left-hand side of the equality, and I realize that that term is actually average variable cost. So what this slide has shown is that the slope of the average variable cost curve is 0 when average variable cost is equal to marginal cost. And since they have different slopes, what that means literally is that the minimum of the average variable cost is where the marginal cost curve bisects average variable cost. We could construct a similar proof to show that marginal cost bisects average cost at its minimum, but it's virtually an identical proof. It's not worth doing. Okay. One of the problems in the practice quiz deals with the fundamental theorem of calculus, so I thought that I'd remind you of it now, lest it be a surprise to you. And applied to this particular situation, what the fundamental theorem says is that if marginal cost is the derivative of variable cost with respect to output, then variable costs are equal to the integral of marginal cost with respect to output. And that derivative is evaluated here from an output level of 0 to some output level y sub 0. Geometrically, what this means is that average cost could be calculated as the area underneath the marginal cost curve. You remember from your calculus course that the integral is basically equal to the area underneath a function. So average cost is equal to the area underneath the marginal cost curve by the fundamental theorem. Now, to give you a simplest possible mathematical example, there was an example of this in the text. There's numerous examples of this in the quizzes, the practice quizzes. So I'm going to illustrate with a quadratic math example. So what I mean by that is total cost, you'll see from the first line to my left, is a quadratic function of output. Now, we're missing the linear term, but that's okay. All that's necessary to make this work in the simplest way possible is cost has to have a quadratic term. So if that's true, I can divide both sides by output and get average cost is equal to y plus 1 over y. I know that the variable component of that, average variable costs, would be y. Average fixed costs would be 1 over y. Marginal cost is equal to the derivative of total cost with respect to output. And if I differentiate total cost, y squared plus 1, with respect to output, that derivative is 2y. Now, I know that average cost is minimized where marginal cost equals average cost, so I could set those two equal, and I can solve for the level of output where average cost is minimized. So given marginal cost and average cost as I've computed them, average cost is minimized at an output level of 1. I could put that output level 1 back into either marginal cost or average cost, since they're equal, to get what those per unit costs are. So I know that marginal cost at output level 1 is equal to 2. So then I get this diagram that's immediately to my left. We have a nice U-shaped average cost curve. Now you'll notice that because cost was quadratic and not cubic, because it was quadratic, average variable cost and marginal cost now are linear. So we get a cost curve that looks like this, in contrast to the ones that we saw one slide back, where cost curve, the cost function would have been cubic in output to give marginal cost and average variable cost that were quadratic. In the long run, you remember John Maynard Keynes said we're all dead, but the serious answer, you recall, is that in the long run, capital is now variable. And what Hal does in the textbook is he shows the long run average cost curve as this red thing, which is the lower envelope of a whole bunch of short run average cost curves. So what you could think of is that each of these black average cost curves represents the average cost for a given capital stock. And then the long run average cost curve is the lower envelope, where for each output level we choose the efficient capital stock. Okay. So quiz problems. First we have Rex Carr, who can choose between 3 methods to dispose of a car. He could pay $10 for a shovel and pay his brother Scoop $5 to bury a car. He could buy a low-quality car smasher, which has given costs, or he could buy a high-quality hydraulic car smasher that's more expensive, but it has a lower marginal cost. So the question is, how many cars does Scoop have to, or excuse me, how many cars does Rex need to dispose of for it to be worthwhile for him to buy the high-quality smasher? So the way that we would compute this is that we have the 3 production methods, which I've denoted here as 1, 2, and 3, and the first one is high variable costs, low fixed costs, and then all the way down to method 3, which is extremely low variable costs but high fixed costs. So I claim there exists some output level where the total cost of using method 2 and method 3 are the same. So beyond that level of output, then Rex wants to use method 3. So I simply set those 2 cost structures equal to each other and find that this is at 300 cars. So if Rex is disposing of 300 cars, his cost is the same. For any output level above 300, method 3 will have a lower total cost. Okay. Mary Magnolia has variable costs equal to y squared over f, where y is the number of bouquets she sells per month, f is the number of square feet of space in her shop. So the size of her shop is a fixed cost. She currently has a shop of 1,400 square feet. The question is, how many bouquets per month should she sell in the short run if the price is $3 per unit? So the way we could solve for Mary's problem, she should sell bouquets as long as the price is greater than or equal to the marginal cost. So if we have her variable costs, her marginal costs are the derivative of her variable costs, and we set price equal to marginal cost and find that Mary should sell 2,100 bouquets. Okay. And finally, Touchy McFeely's production function for comic books is 0.1 j to the 1/2 L to the 3/4. And we have a price for old jokes. We have a price for cartoonist labor. And the question is, what is the cheapest way to produce comic books? So we need to get the cost minimizing ratio of jokes to labor. So the way to do this, we'd actually apply the exponent rule. So from the exponent rule, we know that the proportion of total costs that he would spend when spending efficiently on jokes is going to be the joke exponent over the sum of the exponents, which is equal to 2/5. Right, so 2/5 of total cost are expenditure on jokes, 3/5 of total cost, so that's the labor exponent divided by the sum of the exponents, or 3/5 are equal to total expense on labor. You'll notice that, so we have 2/5 and 3/5. In order to use the exponent rule, what we need to do is generate some sort of equality using those two bits of information that I have. And I claim that the least common multiple between 2/5 and 3/5 is 6/5. So what that means then is if I multiply the joke cost by 3, that'll give me 6/5 of total cost. If I multiply the labor cost by 2, that also gives me 6/5. So if I set those two equal, what I find then is that J must equal to 4L. What that means is for each hour of labor he purchases 4 old jokes. So that'll do it for chapter 22.